Quiet on the set. Hi friends, this is Kat, and today I'm going to show you some magic tricks using SAS. This is going to be a lot of fun. What I wanted to do was give you a little taste of how you can go from exploring a data set to figuring out what might be explaining the target variable you're trying to predict to getting a reasonably good, automatic, quick and dirty predictive model to putting that model into a pipeline that could actually be used as a deployed final model for scoring. Now, along the way, chances are quick and dirty automatic machine learning models are not always going to be the best models. So you may want to add in your own carefully curated, well-constructed model as well. Put it into a tournament, pick the champion, and go with that. So the data set that I'm using today is a bird strike data set. This is a data set that records lots and lots of events when airplanes were struck by birds, which is really unfortunate for the bird, might be unfortunate for the people, but most of the time it actually does not cause damage to the aircraft. We want to see if we can predict what causes damage or what predicts damage to the aircraft when there's a bird strike. And the thing that's tricky and why we want to explore the data with our own eyeballs is that there are variables in this data set that occur after the bird strike or at the same time as the bird strike that would not be good and useful predictors of damage due to bird strike. So let's take a look in the software. We're going to go to Visual Analytics and then we're going to move it over to Model Studio. Let's get started. All right, here we are in the bird strikes data set. And the variable that I want to explain and predict is this indicated damage effect. Now there are three effects in here: impact to flight, indicated damage, and other. The first thing I want to do is have indicated damage, just take a quick look at it. You can see that 91,863 of these flights did not have damage. 7,541 did. So most of these flights that had bird strikes did not actually report damage. If we go back to the data set, the other two variables that could be used as targets, I'm going to go ahead and hide those so that they're not considered as part of the candidate set for my predictions. The first thing I want to do is try to explain it. So what are the variables that explain cause damage versus not cause damage? That's going to be my first magic trick. So right click on Effect Indicated Damage and select Explain. Notice there's also a predict. The predict just enables me to set lots of different factors at different levels and get a prediction. What I want to do is actually just see what are the variables that seem to be most related to this target. So we're going to explain this on a new page. Here it comes. It is developing an automatic machine learning model in the background to try to explain damage. And the number one predictor of damage seems to be wildlife size. If we take a look, we can see the distribution of wildlife size. But down here is what are the groups based on wildlife size by the chance of effect indicated damage being caused damage. You can see up here that we're predicting caused damage. You could also try to predict it the other way around, no damage. But cause damage is more interesting. So you can see the highest predicted probability is when wildlife size is large, and then there are some locations that are especially problematic. Well, there's a whole bunch of them. And that gives us an 81.82% chance of being caused damage. What about not caused damage? If we look at the wildlife size, well, when wildlife size is large, but the aircraft type is missing, so that may be that the large wildlife smacked into something else that's not an aircraft, like maybe a luggage trolley or a window, then we don't have much chance of it causing damage. Also, if the wildlife size is small, then there's a very small chance of there being damage. Let's take a look at the second strongest predictor, number of engines. On the low side, we can see that when the number of engines is missing, or C or S or 2 or 3 or 4, it's a low probability, but here's the interesting one. If the aircraft number of engines is 1, the chances of it causing damage are considerably higher. So it's those one engine aircraft. Let's take a look at the phase of the flight. High probability of damage is when the phase of the flight is in climb, descent, or en route. And a low probability of damage is when the flight is landing or missing. Maybe there is no phase of the flight because there's not a flight. Maybe the aircraft is just parked or it's not an aircraft at all. So now I'm going to show you the next magic trick. This is a mystery model, and it's not something that we're going to want to go take into production. So if we want to have a model that we can actually use and get score code, let's go ahead and change the automated explanation to a machine learning model. I'm going to choose a gradient boosting model. Gradient boosting model is one of several types of what we would call an ensemble of trees. So it uses lots of trees, and what it's trying to do is reduce the error in subsequent trees. And the number one variable importance is cost of repair. Cost of repair, well, if there was a cost of repair, then there must have been damage. Aha! So this gives me some insight. There are still variables in this data set that we should not be using in predictive models. This is why it's so important to have explainable models. So let's take a look. Ooh, there are 3 cost variables. Let's go ahead and take those 3 out. You can see as I remove them, the model is automatically refit. This kind of blows my mind that with 99,000 observations, it can refit a gradient boosting model, hundreds of trees, and it does it just like that. That does kind of blow my mind. Some other variables that we might not want to have included in here. Let's see, are there others? I think I'm okay with these other variables. Notice that it's using the partition ID, which means it trains the model on the training data, and then it validates the model on the validation data, and that's how it ends up with its final model. Another thing we can do is take a look at this iteration plot, misclassification rate. I can change that to a plot that enables me to get better interpretation of the model. One criticism of gradient boosting models is that they might be thought of as a black box. It could be really hard to explain these models, but the partial dependence plot makes this very easy. So here's the predicted probability for small, medium, and large wildlife. What about the number of engines? The predicted probability of damage for single engine aircraft, much higher. What about the phase of the flight? It definitely looks like en route, descent, and climb are where we have the highest probability of damage to the aircraft. The next thing I'm going to do is I'm going to move this over to a pipeline. So I say, okay, I've played around with this enough. I have a model that I think I might want to try to do some scoring with. But I'm also going to need to bring along any data manipulation or data management stuff that I did in VA. And I also might need to do some additional pre or post processing to my model in sort of a pipeline approach. And I need to keep that score code all the way down. Are you ready for a magic trick? Let's do this. Right here, you can see create pipeline, add to new project, and it automatically creates a pipeline that's going to have a node for the data where you can go in and set the metadata for that data set and all of its variables. There's going to be a node for data preparation, any of the work that was done in VA to, for example, compute new variables or create a partition variable or do anything else that you might have done. And then there's going to be the gradient boosting node, which is the model that was developed over, the model that was trained over in visual analytics. And then model comparison, which enables you to sort of assess that model. But we only have one model. What are we comparing it against? There's nothing to compare it to right now. So let's add another model. We're going to add a decision tree, and I'm going to put it right under visual data preparation. And I'm going to set some options on this decision tree. Let's have the maximum depth of the decision tree be 8, and the minimum leaf size for the decision tree, 5 is pretty small. Let's go with 50. And run that pipeline. Okay, in real life, you might spend a lot more time than that deciding on a good custom model to develop and train and fit and compare. And now it's time to compare them. All right, in my tournament, the gradient boosting model wins. I didn't really spend a lot of time and effort on that decision tree, but you might be able to come up with a better model on your own. And you can see in the assessment, we can take a look at these models compared to one another. There are lots of different reports that we can look at. All right, so that's all there is to it. Now you know how to do some magic tricks with SAS as well. Did you like this video? If you did, give it a like. Also, leave me a comment down below. I'd love to hear from you. What did you think? What are some other things you'd like to see in these videos? There are links below if you want some more details, a little more information. And don't forget to subscribe to the SAS Users YouTube channel and click the bell if you want to get notifications. I'll see you next time. Thanks for watching. Bye.